Okay, so you're going to have to put your imagination on today. Okay, a little bit of an imagining. If you have this region above the x-axis, and if you can imagine that the x-axis is like a swivel stick, okay, it's spinning, you could spin something around it. Do you remember that our x-axis is fixed and we give this shape a spin and we spin it around the x-axis super fast? What shape is formed when that thing gets spun around the x-axis? Kind of like arch. Okay, if you take ceramics, I feel like you have a better visual idea of what this is because you've been on a wheel. And the wheel in ceramics is a vertical wheel because the thing is spinning this way, but we're talking about spinning it this way. Okay, I just about was to write on my iPad with this. All right, so if we spin this, look at the reflection of it upside down. So it's going to look like that, sort of. Okay. But it's been spun, so this has got to have some kind of roundness to it. So to me, that sort of looks like a pot, right? Or a vase or something like that. Okay, because it's been spun around. We're spinning things or shapes around the x-axis. Somebody you could take your sweatshirt string out of your hood. Can you get it out easily? No, that is hard to put back in. But if you take it out, right, you hold a sweat. Oh, this might work. Right? Shape? What is it? Right? What is this shape? Okay. Ooh, yeah, a lot of people think it's a parabola. It's not. It's called a hyperbolic cosine. But anyway, because gravity pulls on it and makes it not a parabola. But anyway, but if I spin this, okay, can you see the shape that's being formed in the air, right? Yeah. Okay, the ends are pointy because this point stays fixed, but this is in the air, it's shaping, pulling out a three-dimensional round object with pointed ends, almost like a football, right? Okay. All right. Okay, so if we just did that one, we had the x-axis, and we had a arch that was fixed at either point, and we spin it in three-dimensional space. Okay, then it forms the perfect reflection. Ooh, I'm having trouble. Okay, but it's round. But this shape did particularly have pointed ends. So yeah, kind of a football type shape. Either way, if I took a knife and started cutting this and slicing it, what shape would the slices be as they start to fall away, assuming that I'm slicing them in slices starting maybe at the origin and just slice, 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 slice. What shape are the slices? They're all circles. Okay, anything that's rotated around the x-axis is going to have cross sections. A slice is a cross section, which is circular. And every circle has a different radius. So we go back to the first one, okay, that first slice. But then the slices get narrower as I reach the neck of that jar, if you picture it. And then the slices start to widen. Okay, these are called cross sections, so the circular cross sections. And then they start to get smaller as we reach the base of that shape. So you start with circular cross sections. That same thing would be true with the football type shape. It would start with very small cross sections, get to its widest point in the middle, and then start to diminish in size again. What's changing about all of these slices is the length of their radius. The radius is always changing. And so that's one thing we have to keep in mind, is that the radius is always different as we move across the shape. What stays the same about every single slice? Okay, what would stay the exact same? The thickness of the slice. Okay, it's like if you take a bunch of coins together, all of the coins, all of the pennies, all have the same thickness. So the width of each one is always constant. Okay, the more accurate we will be is if these slices become thinner and thinner and thinner. And so the width is going to be expressed as the thinnest of all, which is dx. It's the thinnest slice along the x-axis. When we start rotating things around the y-axis, then we'll have our slices be dy instead. But this is going along the x-axis. All right, so we're setting this up. Now, how would you make one of these things have a hollow core? Okay, right now these things are solid. All right, how would you make it have a hollow core? In other words, what if I wanted to carve out a chunk out of the center of this so it had a hole in the middle? What would the original shape have looked like if that hole was carved out of the center? Do you remember what the original shape? Okay, no, not a slice. A slice is going to look like a donut. What would the original region that we rotated looked like? Well, it would, instead of looking like all the way down to the x-axis and then it went like this and that, okay, instead of going all the way down to the x-axis, what's it going to do? It's going to stop, and it's going to, the original region would look more like that with the x-axis. So there's going to be a gap between the original region and the x-axis. So if there's a gap, there's space between what you're doing and the x-axis, you're going to have a hole in the center, which means all of your slices will be more like bagels or donuts or washers or something with a hole in the middle. And so you're going to watch where your original region is. The top region we call R with a capital, because that is going to be the outer radius of the shape. R stands for radius, and we use capital because it's the larger of the two. It's the outside one. Little r we're going to use for the lower curve, which is forming the radius of the interior. So you have an exterior radius and you have an interior radius. So this capital R is the exterior radius, and the little r is the interior radius. So to find the volume, well, so let's set up what we know about area. We have the exterior area, which because it's circular in shape would be pi capital R squared. And we have the interior area, which again, because these are all circular in shape when you slice them, is going to be pi little r squared. And so if we want to take out that core and we want to make it hollow on the inside, we will have pi capital R squared minus pi little r squared. And if we want to turn this into volume, we do the exact same thing that we did with all of our shapes yesterday. These shapes happen to be washers or bagels or donuts, if we want to call it that way. Okay, this is the area of a donut. Washer is the official word, okay, because the slice here, all slices are going to look like this if you turn them sideways and take a look. R is going to represent the distance to the outside, and little r will represent the distance to the inside. And the subtraction of the two would give you the area of the ring that's left. So over the weekend, how did you turn that into volume? Make it the integral. All right, and that's exactly what we're going to do, is to make this be a volume. We are going to take the integral of this quantity And then we add dx to show that we're going along the x-axis. So it is pi times the capital radius squared minus pi times the lower radius squared, the subtraction of the two along the x-axis going from A to B. All right, so let's do some actual problems. Find the volume created by y equals e to the x and y equals half rotated around the x-axis on bounds 0 to 2. So I recommend drawing this in 2D before drawing it in 3D. My two dimensions, e to the x will come up this way, go through the number 1, and then shoot up to infinity. There's my e to the x graph. Always goes through 1 on the y-axis. Y equals half is a horizontal line. That's just going through half on the x-axis. And I'm going from 0 out to the number 2. So let's say that our region looks like this. That's my two-dimensional region. When I spin this around the x-axis, because it has a gap between its bottom edge and the x-axis, it will have a similar gap. So the reflection or the rotation will look like that. The edges will be round because it was rotated around. So I'll have an interior circle and an exterior circle on the short end, and I'll have the same thing on the opposite end. And I'll have a round piece. Okay. So it's got a hole in the middle. I usually like to try and kind of make my front edge of this piece. I'll make some rounded. Boy, it's really sticking. All right, there we go. So I like to do that to show that it's solid on the outside, but it's rounded on the inside, and I've got this interior thing bored through it. Well, that's the visual. You're not going to be graded on your pictures, all right, but you will be graded on how you set up your integral. So we need to set up what our pi big R squared is. So our big R is formed by the outer edge, which was e to the x. So that'll be e to the x quantity squared, or pi times e to the 2x. Be another way of saying that. Our pi little r squared would be formed by pi times the half, which is the lower bound, or 1/4 pi. And so if we want to make this into an overall volume, our volume would be the integral on the boundaries from 0 to 2 of parentheses around a pi times e to the 2x minus 1/4 of pi dx. I'll probably factor my pi out to the front because pi is common in both of them, and I don't need to have the pi. So if I pull that out, I can just work on e to the 2x minus 1/4. And then I can integrate each of those without too much difficulty without my calculator. Notice I haven't used my calculator at all. So you're expected to know what e to the x looks like as a shape. And half, you're expected to know what it looks like as a shape. If you're going to get crazy shapes with crazy intersection points, well, then you get your calculator. But we don't need that for this. So the antiderivative of e to the 2x is e to the 2x divided by 2 ln e. And the antiderivative of 1/4 is 1/4 x plus the constant c going from 0 to 2. And then at that point we would evaluate. I'm not going to finish this problem because that's not the point of our lesson today. The point of our lesson is to learn how to set it up. It's not to necessarily learn how to finish. Okay, do you have any questions about that so far? Okay, let's try another one. All right, so let's do the same thing. The instructions are going to be the same. I'm not going to rewrite the instructions every time, but we'll have two different functions. We'll have f of x being equal to cos x plus 2. We'll have g of x being equal to 1. And the interval is going to be negative 2 to 2. And we're going to be on the over the x-axis or around the x-axis. So all of that is still the same. We're finding the volume. So let's have a good 2D understanding of this. So cosine x plus 2. I expect you all know what cosine x looks like. That you have a good understanding that cosine x is shaped like this. And when you bump cosine x up 2 whole units, right now, this is a scale of 1. So if I move this whole thing up 2, the entire thing is going to be above the x-axis fully because the max will get shifted up to 3 and the min is going to get shifted up to 1 and the whole thing would be shifted up. So my new drawing of this, I'm going to take all that off, is my graph would be up here, fully above the x-axis. So that'll be 3, that'll be approximately 2, and that would be 1. I also need to have the number 1, which is just a horizontal line coming across here. Okay, we know that these values are pi and negative pi, but my interval is only from 2 and negative 2. So my interval is cutting off the ends. It's not going all the way to the intersection point. It's cutting off those little end edges, and here is my original region. So that's what's getting rotated over the x-axis, and it's going to have a gap, a center, that's missing. So visually, when I rotate this section over, I do have 2 edges, and then shaped like cosine. And then an outer edge and an inner. Ooh, that was poorly drawn. Try that again. Outer edge and an inner. Hello. And then we'll have the same on the outer edge. This one kind of always looks to me like sort of a bead that I would string with a hollow center, cut through the middle. All right, so having the understanding of that, let's at least set up our function. So we'll have the outer, which would be pi capital R squared. The outer was formed by the cosine function, so that was cosine of x plus 2, quantity squared, which is going to be cosine squared plus 4 cos x plus 4. We'll have the interior, which was just the number 1, so that'll be just plain old pi. So my volume would be set up as the integral of that on the bounds. Now, this does have symmetry, so I'm going to use symmetry to my advantage. I'm going to double the integral from 0 to 2 rather than doing the whole integral from -2 to 2. And I'll have pi. In fact, how about I just take my pi out right now since I'm going to be factoring it out anyway. So I'm going to put 2 pi out front. That would leave me with cos squared plus 4 cos x plus 4 minus, and if I take pi away from that, I'm just left with 1. And then I can simplify 4 minus 1 and make it 3. So I'll have 2 pi of cosine squared. Actually, back this up a minute. If I'm doing this by hand, cosine squared needs an identity. The identity for cosine squared is half plus half cos 2x. You've seen that in a previous homework assignment. If you've got your calculator, you'll be allowed to do it straight with your calculator. 4 cos x is fine. I know how to do the antiderivative, and then 3 at the end. And then keep going. Any questions on that one? We've got one more. Y is what? Last one. If you're given a single curve on a non-symmetric boundary, so here's x squared. X squared we know is a parabola. The boundary is non-symmetric, but we're still going over the x-axis. So we can't use symmetry here to our advantage, and we don't have a lower bound. So our original parabola is going to look like this, from -1 to +3. And this fully touches the x-axis. So there's no gap between this region and the x-axis. It's touching the x-axis all the way down. So my original region is going to look like this. And then touches at the origin. So when you rotate that, this is not going to have a hollow center. The rotation will come to a squeeze at the origin and then fan back out again with rounded edges on either end. But there is no center piece that's carved out. So I don't have to worry about subtracting the little pi r squared because there isn't one. There isn't an interior piece here. This is fully solid. Okay, it's all the way solid. So my thing set up will just go from -1 to 3 pi, and I don't have a middle piece to carve out, so it's going to be the radius squared dx, and that's it. So this is when you don't have a hollow center, the setup is a lot easier, so you don't have any subtraction that you have to do.